Hey, so this is the video overview of the Python version of the Lab 5 forward and inverse kinematics of a two-link arm. If you've chosen the Python version, I'm going to assume that you are vaguely familiar with Python. If not, I would recommend MATLAB as that is more comprehensive at this level. Anyway, if you'd prefer this one, we'll keep going. First, I'll do a quick review of how matrices are constructed in Python. You're going to need the NumPy library. And the way we do this is we're going to declare an array. And then we have square brackets. And then for every row inside is another pair of square brackets. So 1, 2, 3, 4. We need commas in between. And if we go ahead and print x, and then we run, one, two, three, four. Cool. We should be able to also add to arrays if you need to. There we go. Each one is added by 2. We can subtract if we wanted to. Cool. When we multiply by a single number, it'll go ahead and do element-wise multiplication. But if we want to do a matrix multiplication, for instance, y is equal to it needs to be of a compatible size. A 2 by 2 can be multiplied by a 2 by 2. And there we get that. But keep in mind that matrix, actually, that is also element-wise. Sorry, the correct matrix multiplication here is the @ symbol. There we go, that's correct. So we took the first row, multiplied it by the first column, and then added them together. So 1 times 1 is 1, plus 2 times 2 is 4, add them together 5, and so on and so on. Keep in mind that in matrix multiplication, the order of operations is very important. X times y is not the same as y times x. There we go. When you'll want to build arrays for your transformation function, we can do that too. That is using dot block. We can print dot block, where our first row consists of x, y. I believe we have to do y dot t. So t is a transpose. So this right now is a, no, we should be fine. Because this is a column, it can be added on the end of a 2 by 2 vector, and that should be fine. So let's run that, see. There we go. We see a 1, 2 is pasted as an extra column at the end there. And then if we wanted to do our 0s and 1s afterwards, 0, 1. Go. And that would be your transformation matrix. It's actually in this case not quite correct because there's a special property of rotation matrices that the magnitude of any row or column should be 1 because it's made of cosines and sines of the same number. So 1, 2, 3, 4 is not a proper rotation matrix, but if we did say a rotation of 90 degrees, where cosine of 90 is 0, negative sine 90 is -1, then we have +1, 0. If our translation was 1, 2, and our rotation was 90 degrees, this would be our transformation matrix. There we go. And then say we wanted to multiply that transformation by a point. We have a point of x5, y, it's column vector, so x5, y3. We can't do our multiplication like this because a 3 by 3 can't be multiplied by a 2 by 1. Just does not like it. So in this case, we add a 1 to the end, and the 1 won't change our math at all. It's just adding that extra dimension so that the multiplication is valid. Cool. So a 0.53, which has been rotated 90 degrees and translated 1 in the x, 2 in the y, comes out to 0.27, negative 27. There's that. And then to make a function in Python, we have def, and then whatever we want to name our function. So if it was demo, and then here we would have our inputs if we have any. So if we did this as px, py, and then our indentation matters in Python. So we do that. And then we would come down here, and instead of printing, if we return p at p, and then we can print demo of 1, 2. We should get the same number. There it is. So that's how you would build a function in Python. You can import full files into Python. So basically, if I wanted to take any functions that I've written here in demo and bring them into a different script, I would say import. So here I've imported my functions in order to run the testing script. And with this is on your computer, it'll import whatever rote2d is in your same directory. So that's where you want to save your Python file. And then the way that the testing files are formatted for Python, it's in comma separated values. And this tests folder would have been in your zip file that you downloaded from Canvas. So your inputs here, each row is a different test. So here, the first rotation 2D gives, this is your first theta. You're going to build a rotation matrix from that and multiply it by the rotation matrix with this theta. And then it's going to give you this output for your rotation matrix. And the test script should handle parsing these CSVs for you, but if you wanted to know where those numbers came from. And then similar with the transformation. Transformation, you have 6 inputs per test. Here is theta 1, here is x1, y1, theta 2, x2, y2. It's going to form those 2 transformation matrices, multiply them together for this transformation matrix, which is the 3 by 3. For the forward kinematics, you have 4 inputs. We have L1, L2, theta 1, theta 2, and based on the 2-link arm that we've covered in lecture, you want to build and multiply the transformation matrices. Your output should have 4 points. Here is the XY coordinate of your tooltip of the arm, which is this very end point here, P. And this is the XY position of your P2, which is this middle point here. And you will form those by first doing the rotation matrix of theta 1 with a translation of 0. Then you'll multiply that by the rotation of theta 2 with an X translation of L1. no y here. And then finally, you'll multiply it by a rotation of 0, which is 1, 0, 0, 1, and an x translation of L2. So the way this works is first, we're starting at the origin with our normal axes. Then we rotate. So we've found where these vectors are. And then we translate and rotate. So we find out where this point is and also where these vectors are pointing. And then lastly, we can extract this last point here after our final rotation matrix. Transformation matrix. And then you want to be sure that those are in order. And then you will use our functions that we just learned about. You'll build one for returning, let's see, if we had 2 outputs. So in this case, if I wanted to say P2 equal to T at P, I can return 2 values by saying P2 at 0 followed by P2 at 1. There's 2 of those there. And then I could also say Px, Py is equal to, and then say print Px, Py. Now I can show that they're separate variables being returned. There we go. Cool. And then for your inverse kinematics has 4 inputs. We have L1, L2, your destination X, and your destination Y. So based on these 2 link lengths, solve for the 2 thetas that would get the tooltip at this point. And then here are the 2 thetas for your output. And then there's also going to be a third value. It's a Boolean if the point is reachable or not, because there's certain situations where you might give it an XY point that's not possible. For instance, if your links are not equal, it's not possible to reach the origin. So that would have a reachable of 0 for 11. And then those are actually all the same. That's fine. So stuff like that. Something a little different about the inverse kinematics function. You will need to import both math and CMath. CMath helps with the arc tangent, arc cosine type things. And then regular math just helps you do other stuff. You'll want to use the POW function instead of just the caret for squaring things, because some of these L1, L2s might not be integers, and it doesn't like the caret when you have floating points. And then I would definitely, when you are trying to implement these equations, I would split them up so you can help solve them by hand easier. For instance, the first thing you'll do is solve for theta 2. I would split these up into numerator and denominator and work there from there. That way you can help solve it better. Let's see some other tricks here. I'm going to scroll quickly so you can't see it as well as I can. Oh, yes. So here when we're solving, if it happens to be, if the denominator is 0, you're going to get a wonky result because that's, you can't divide by 0. That's undefined. So before you get to this step, you might want to check if denominator equals 0. In that case, the 2a tan of that number will be pi. You can go ahead and hard code that if you want. That should help with any errors there. And then when we take a look at, there we go. When we solve with CMath ATAN, if it has a complex number, it's going to have a member of imaginary. You'll want to check if that imaginary is greater than 0. Sorry, the absolute value of the imaginary. If that's greater than 0, you've got an impossible final coordinate. So that's how you'll solve for that. And you'll have to check for that after theta 2 and theta 1, just to make sure. And then same thing here, you want to split theta 1 calculations up. I would recommend splitting it into psi and alpha and going from there. I don't know if you guys have talked about the elbow up, elbow down different solutions, but we only care about one of them. So just return whatever comes first. So that is the inverse kinematics function. Let's see here for your drawing script. Come on. So you'll have to import all your functions, import NumPy. You also need OS for some of the input stuff, and then we're going to be using the matplot library so we can plot our stuff. First, you'll build your array of points, give it some link lengths. You'll need to pre-allocate array. So every coordinate here will have a theta 1, a theta 2, a p-tool, and a p2. And we'll be using those here in a second. But for every coordinate, it has one of those, so you'll need to pre-allocate arrays. You'll loop through. You'll call inverse kinematics to find the tooltip for the given coordinate. And then you will run the forward kinematics so you can get the P2 position as well. And then it'll take those P2 and P-tool arrays, and I've created the function that will write your video for you. Just have to name your variables, name your video. And then I've gone ahead and plotted your X and Y versus time for you, and then saved it to a picture. You'll have to follow that kind of format to plot theta 1 and theta 2 versus time. And then what I'm looking for your paths is something complicated or pretty or interesting, and those will get you more points. If you're too basic, then you might not be putting enough effort in, so that's going to get you some less points. And that should be it for this the Python version of Lab 5.